So we started talking about sequential logic and how sequential logic added in a new element into our design, which we say, okay, I have my sequential logic that's going to occur. This sequential logic has an input, it has an output. Inside it, I was going to use some combinational piece that we really have spent a lot of time developing. So we put input in, we put the output coming out. And then I said, I needed some form of memory where this memory is going to take something from the combinational piece and it was going to provide some type of feedback into our system. Okay, so now what we really need to kind of look at is what is this memory unit? Well, when we talk about the memory, this is going to be very unique in that what we're looking at is trying to figure out a way to have a circuit be able to remember something that has occurred. So this is a memory item. A lot of times when we get down to these basic little symbols here, we're going to refer to it as being a flip-flop. And a flip-flop, for our purposes, every time we see flip-flop, we are looking at it being a 1-bit memory unit, where all I'm able to store is one small piece of information. And if I start developing sequential logic that becomes more complex, involving more pieces of information to be saved, I would just keep adding on these extra flip flops. Now, when it comes to flip flops, there's a number of different flip flops. There's at least, well, 4 different types. We're only going to focus on one type in this example right here. We're going to say that a flip flop for us, or memory for us, we're going to view it as being what is called a D flip flop. Where the other way you can kind of see it is abbreviated as a DFF, a D flip flop. Now, in here, what is a D flip flop? Well, a D flip flop is going to have items that we have already seen before. It has, let's call it Q, where just Q is our output. It has an input, let's call it D. And right now, we're going to add in a third item in a little bit. But first, let me start off by explaining what it is that we want this memory unit to act like. How do we want the memory unit to act like? Is let's base it off a characteristic table. So this is a little bit different than a truth table because I'm just going to explain what it is that I want the memory to evolve into. Where we're going to take our input was D, we're going to take our output Q, and now I'm going to put a star next to Q. Where for us, this little star means next value, or it means the future savings of what it is I'm going to put into there. Now, what we're going to say is if my input is a 0, I want the future value of what I'm futuring going to store to be a 0. If my input was a 1, I want what I'm going to store into the future to become a 1. Now, in here, what is missing from this characteristics table, what's missing is when do I save? When do I decide I need to update memory? Do I do it continuously or am I going to do it periodically? Do I want it that memory is always keeping up or do I want to allow memory to allow the combinational logic to settle down? Well, what we're really going to do is we don't want to save instantaneously all the time. We want to save on a predictable schedule. That predictable schedule, we'll see if we ever see a triangle on one of these little block diagrams, that always is going to refer to as a clock. And this clock mechanism, that is the controlling of when we save. So I will decide when to save based off this clock. Now, if you're ever into any type of technology, like if you build your own PCs or you look at like technical specs on like a phone, on a gaming console, you will always see stuff referred to this clocking. The clocking is that we have a clock frequency. And this clock frequency, you usually see it depending on what type of device you're working on. You might see it as something like it's 50 megahertz, or maybe you see it as something like 1 gigahertz. Well, this items kind of tells us the speed of our circuit, kind of gives us an idea of how fast that circuit is running. And it is this clock frequency that is controlling how fast our memory is saving. So as we can say how fast I'm saving, what does it mean? What does this clock look like? Well, the clock is going to look like a series of zeros and ones. And it's a series of 0 1s that follows a predictable pattern. So in this clock, let's say I was doing a clock of 50 megahertz. Well, this 50 megahertz, each of these pieces on these clocks, here in purple, these are all when the clock is 0. Well, all of those 0 pieces has some type of time to them. So let's say we are low for 10 nanoseconds all the time. So 10 nanoseconds is always the amount we're low. Then let's say like here in orange, I'm going to be high a set amount of time. Again, we're going to control a predictable pattern for how high we're going to be. So the high, let's say it's 10 nanoseconds, 10 nanoseconds, 10 nanoseconds. Well, if we look at this, we can say, okay, what does our clock look like? Our clock is a series of zeros and ones where we know how long each of these took place for. How long did each piece take? 10 nanoseconds, 10 nanoseconds, 10 nanoseconds, 10 nanoseconds, 10 nanoseconds, and 10 nanoseconds. We set up how long we needed all of this time to rely on. Now in here, we're going to see that it's always a pattern that is repeating. And for us, let's just take in green here from the start of orange to the next start of orange, start of orange to the next start of orange. You know, this would have repeat one extra time. Well, we're going to call this a period. And we said that we wanted this clock sequence to be periodic, where the entire time is 20 nanoseconds, 10 of the orange, 10 of the purple, 10 of the orange, 10 of the purple. Well, this 20 nanoseconds ends up being our period. And for us, our frequency is 1 over the period. So if we say we're 1 over 20 nanoseconds, that's also the same as saying we're at 50 megahertz. All right. So when you see that your cell phone runs at 1.5 gigahertz, you can take that 1.5, take the reciprocal of it, and you will get, some idea of how fast you're saving on every piece of the circuit. That's going to be, fairly fast of the amount of time we're switching between zeros and ones. So how do we use these zeros and ones? Well, let's go back to our example of being in a room with the lamp on the ceiling. We're shining the light down. We have our little touch sensor that we're manipulating. And in here, what we need to decide is at some point inside this wall socket here, we're going to have our circuit. And we're going to tie the circuit up with some type of clock mechanism. And now this clock mechanism is going to be, how fast do we need to save our data. Well, what's our data in this example? What is the data? Well, for us, our data is, did we touch the system? Touching the system means we have a new light value. Our light was off, now our light is on. Our light was off, our light is on. So this new light is our data. Now, what speed do we need to set our clock to? Well, the speed is going to be how fast do we expect our light to be switching. So let's just take, for example, here's my sensor. I'm going to be able to detect a touch. We have somebody's hand that's going to be placing it onto that sensor, that little cover plate for that replace our light switch. Well, we can say, how many times a second could one touch this light switch? So right now you can try to think of that yourself. Take your hand and let's just say the table you're sitting at is the touch sensor and give you 1 second. How many different times can you tap it? Now, that many times we want to tap it, we can say, if I wanted to take the, average person, do I want to take the slowest person? Do I want to take the fastest person? If I was to take one of those people and say, I want to be able to maintain that I could see that tapping always being done and quickly update the lights on the ceiling, how many times do we think we could do it in a second? Now, this frequency, we can kind of view it is, this is the number of touches per second. So if I say, I want a 50 megahertz clock, 50 megahertz means I'm doing 50 million touches a second. Now, do we think that's going to be physically possible for a human being to touch, that sensor 50 million times? Likely not. Our cell phones are running at, let's say, 1 gigahertz. Do we think we're going to touch that light sensor 1 billion times a second? Likely not. So you can see that, for us, this frequency is going to be fairly low. Do we want it to be more than 1 hertz? 1 hertz being that I'm doing 1 touch a second. Likely we're able to do more than 1 touch. Do I want 2 hertz? 2 touches a second. 5 hertz, 5 touches a second. There's going to be some time that I'm going to be able to fix to that. Well, what does that mean for us? Is if I take this clock signal, I'm going to identify a spot on where to save. The spots we're going to talk about is, I'm going to highlight it in yellow. In this item, we talk about it being the rising edge of the clock. So on the rising edge of the clock, you see that we go from a 0 to a 1. We go from a 0 to a 1. A 0 to a 1. Well, our D flip-flop only saves on the rising edge. It's going to save at that one moment in time. So for us, let's say we're running at 10 hertz. We decided that's going to be how fast we want to update. For us to change the light from off to on, our hand has to be touching at the exact point we have a rising edge. So the hand must be on the light, the touch sensor. So if we do it 10 times a second, within 1 second, I was going to look at that touch. Was it located being high? So, how long is it going to take you to flip that light switch on? Are you going to be so fast that you can touch it and not fall on another rising edge? Likely, if you're, walking in through the door, you just finished coming home from school, finishing work, you're going to put your hand to turn on, the hallway light. You might leave your hand on there for a couple of seconds. Well, do you want the light to switch on and off real fast? Maybe not. So then you might back off to say, let's give it a 1 hertz circuit and say, I expect somebody to touch only once per second. Likely you're going to be able to pick it up. Or, if we have like a little CPU inside this circuit, we can have some algorithm to say, see that you have to touch and let go in order for it to recognize that you want the switch to change. As we start adding in this clock frequencies, there's going to be a little bit more logic that we're going to have to put into our circuit in order for it to be created. All right, so that gives us the idea of what a flip-flop is.